So, hi everyone. We were discussing GATE 2019's paper, Inorganic Chemistry part. So, today we will start our discussion with solving this question number 43. It came in GATE 2019 paper. So, the question is, I'm audible, right?
Yes, ma'am.
Yeah. The question is, the rate of the following redox reaction is lowest when X is. This is the given redox reaction. Cobalt is in plus 3 oxidation state, which is coordinated to 5 ammonia ligands, and there is one more ligand, X. And here, uh, chromium is the other metal complex. It is in oxidation state plus 2 with 6 coordinated water ligands. So this this redox reaction is taking place between these two metals. Now cobalt from plus 3 oxidation state, it is going to plus 2 oxidation state with 5 coordinated ammonia ligands and one water ligand, and chromium from plus 2 oxidation state is going to chromium plus 3 oxidation state. So here oxidation is taking place, and in this case reduction is taking place. And here, after oxidation of chromium, it is coordinated to 5 water ligands, and X is now transferring from this cobalt complex to this chromium complex. So they have asked the rate of the following redox reaction when redox reaction is lowest when X is option number A water, option number B ammonia, option number C Cl minus, and option number 3 M3 minus. So in coordination compounds, these redox reactions can take place by via two type of mechanisms. One is outer sphere mechanism and the other one is inner sphere mechanism. So the basic general differences between these outer sphere and inner sphere mechanism is that in outer sphere mechanism, both the complexes are inert in nature mostly, and there is no bridging ligand present, and no ligand transfer is observed after the reaction in the redox reaction. Whereas in inner sphere mechanism, among the two complexes between which the redox reaction is taking place, one of the complex is inert in nature, whereas the other is labile. There is presence of a bridging ligand, and ligand transfer may or may not take place in these type of in this redox reaction which is taking place via inner sphere mechanism. Now, ligand transfer may or may not take place in this mechanism, but if we see that there is any ligand transfer taking place, then that reaction is definitely going by inner sphere mechanism. Okay. So here, as we said that both complexes are inert, and in this one complex is inert and the other is labile. So what is this labile and inert? So this comes from like kinetic stability. If a complex is kinetically stable, we call that inert, and if it is prone to this ligand substitution type reactions, we call them labile. So inert complexes are those in which, like here, the complexes which are given are octahedral complexes. So inert complexes will be those in which we know that in octahedral crystal field, the degenerate d orbitals split into two energy sets. One is T2G and the other one is EG, where T2G is GXZ, GYZ, or dxy, and Eg is dz square and dx square minus y square. And if we draw this octahedral complex, so this plane, and these are the two axial positions. So this lies with the like in the direction of this Eg. Okay, so whenever there is an electron present in the Eg orbital of the metal, repulsion will take place because ligands will approach from this side, and because of that, whenever there is an electron present in the Eg orbital, then that complex is labile in nature. So electron in Eg orbital decays, that is labile. Okay, and if it has a failed D3, that is 3 electrons in T2G, and no electron in Eg, then that ligand will be inert in nature. But also, if there is only one electron, like let's say it is a D1 system or a D2 system, then also it is labile. Then also it is labile because there is like room for electrons to come in this T2 orbital, T2G orbital as well. So labile complexes are those in which electron is present in Eg orbital and for D1 and D2 system, whereas inert complexes are those in which either it is G3 or high spin or low spin D4 system or D5 system or D6 system. Okay, low spin D4, D5 and D6 and D3 system. Okay, for this it will be inert in nature. Now here in this given redox reaction, we will first check for this cobalt complex. So cobalt here is in +3 oxidation state. Cobalt is how many electron system? It is G7H2, right? So cobalt, if it is in +3 oxidation state, that means it is a D6 system. And we know that ammonia is a strong field ligand. Therefore, here all the 6 electrons, because it is a strong field ligand, therefore spin pairing will take place, and this will be the electron splitting. Okay, so from this we can see that there is no electron in Eg, so this is inert. And if we look onto the chromium complex, which is chromium 2 plus, so chromium is a D5S1 system. Chromium 2 plus means it is a D3 system. No, sorry, it is a D4 system, right? So 1, 2, 3, 4, 5. So D4 and say water, we know that water is a weak field ligand. So this will be a high spin complex. High spin complex means no spin pairing will take place. So 1, 2, 3 and 4. So here electron is present in Eg orbital. So it is a labile complex. So this is one factor by which we can say that this reaction, this redox reaction is going via inner sphere mechanism. And the other way by which we can be sure that this is going via inner sphere mechanism is that I told here that if ligand transfer is taking place, that means it is going via inner sphere mechanism. So here we can see that first this X was coordinated to cobalt, whereas after the reaction, this X is coordinated to chromium. So ligand transfer is taking place. Hence, this reaction is going via inner sphere mechanism. Now, in inner sphere mechanism, what happens is uh, first there will be one like here, cobalt is in +3 oxidation state. It is having 5 ammonia ligands, and there is X. Okay, say 3 plus or 2 plus, and chromium 2 H2O whole 6 2 plus. So after this, what happens is this X If it is a bridging ligand, then NH3, CO, X, and then chromium 2. Oh, chromium 2. Okay, so before this reaction, what will happen is, as we said, that this will be the labile complex. So since it is labile, it will lose one water molecule and it will become coordinatively unsaturated. Okay, it will become coordinatively unsaturated, and now therefore through this X ligand they can bridge and it will be H2O whole 5. Okay. Then what happens? Through this ligand, the electron transfer takes place from one metal center to the other metal center. So now electron transfer will take place and cobalt will now become in plus 2 oxidation state and chromium will go to plus 3 oxidation state with 5 water molecules, and here it is having 5 ammonia molecules. Okay. So after this transfer, next cobalt to NH3 will be there. Now since cobalt 3 NH3, it is a coordinatively unsaturated complex. Since therefore the water molecule which released in the first step of the reaction, that will coordinate with this cobalt and it will give this complex, and the other complex which we will get is chromium 3 H2O 5 and this X. Okay. So this is the mechanism of inner, like this is how inner sphere mechanism takes place. So now coming back to the question, that is when the rate will be slowest for this redox reaction. So here, if it is a good coordinating ligand, if this X is a good coordinating ligand, then it will coordinate uh, properly and electron transfer can go through this. Now, if it is a bridging ligand, that will be the reaction, the electron transfer will be very much like it will let the electron transfer go fast, and therefore for bridging ligands, which is in this case Cl minus and N3 minus, they are bridging ligands. So when Cl minus or N3 minus is present, the electron transfer by these two ligands will be faster, and they will do this electron transfer between cobalt 3 and chromium 2 faster. Okay. Whereas if it is H2O and NH3, they are not bridging ligands. So in these two cases, it won't be that faster. So first we can eliminate these two options, C and D. For them, it will be faster. The reaction rate will be faster. Now we have to compare between water and ammonia. So how can we compare? We know that if we see the spectrochemical series, then water comes like water is less is weak field ligand compared to ammonia, right? So therefore, because of this strong field ligand, this complex, this cobalt complex here, there will be more delta O, and it will become more inert in nature. Okay, so if there is a more strong field ligand, it will make this complex more inert, and therefore the reaction, like the tendency of doing this reaction will decrease further. So we can compare water and ammonia ligand by this way, and from that we can understand that in ammonia case the redox reaction rate will be the slowest. Okay, so for this question the answer, that is what is the slowest when the reaction will be slowest. So it will be slowest when X is equal to ammonia. Any doubts?
No, ma'am.
Clear to everyone?
Yes, ma'am. Very excellent explanations.
Yeah, thank you. Okay, so next we will move on to the next question. This is the official site of GATE NPTEL, so you can go to this site. It's in and watch the video. And as I am taking every Monday 7 to 8 p.m. classes, now I it have been recorded. Like the class links are also available in the website. You can go through the classes as well. Okay, if you have missed any. Okay. Next, moving on to question number 45. Okay, so question number 45 is the number of possible optically active isomers or isomers for the following complex is. So we have to write there are how many how many possible optically active isomers. So this is a cobalt complex. Okay, two cobalt centers are present in this and it is bridged by one NO2 and one NH2 group, and there are two ethylene diamine moieties present on both the cobalt centers. So we have to find out there are how many optically active isomers. So let's draw this complex first. CO, NO2, NH2, CO. Okay. Here ethylene diamine means NH2, CH2, CH2, NH2. Okay. So it is like N, N. So NH2, CH2, CH2, NH2 is a bidentate ligand, okay? Because there are two nitrogen present and it can coordinate with both of these nitrogens. So it is a bidentate ligand. Now we know that what are which complex will be optically active? The complexes which don't possess any plane of symmetry. So the condition for being optically active is that no plane of symmetry should be there. Okay, no plane of symmetry. Now we can draw this complex like CO. Okay, sorry. So we can imagine this as one is a upside bond and the other one is going down the plane. NO2, NH2, CO, and N. Okay, so one possible isomer of this is this orientation, but here we can see that a plane of symmetry lies here, right? From where the plane of symmetry will be there? Anyone? Okay, so if we consider this complex, if we can draw a plane of symmetry from here, right? From here, if we cut this complex, both sides it is equal. So this one is not optically active. Now, if we draw the other conformer, that is CO, N, 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 NO2, NH2, CO. Okay. So the other way can be that the ethylene diamine is coordinated like this. Okay. So this and this. So now if we have this complex, then there is like no plane of symmetry in this molecule. We If we see it like this, we may think that there is a plane of symmetry in this case also from lying from here, but that is not the case because here one nitrogen is present upside and the other one is down. So if you can imagine that this complex is not having any plane of symmetry. And since this geometrical isomer of this complex is not having any plane of symmetry, therefore it will be optically active. Okay, so this complex is optically active. That means we will have one D configuration and one L configuration. Optically active means we will have a plus minus, right? So the total number of optical isomers for this complex will be 2. Okay. So now, if you see the answer key for this paper for this question, you will see one option is 2 and the other like one correct answer is 2 and 4 is also a correct answer. So what I think is 4 also they gave us correct answer because here in NO2 you can see that this cobalt can coordinate via both N or O. Okay, because oxygen can also coordinate. So maybe if oxygen is coordinating in this case, for that case also we will get that will be optically active and plus minus will come for that also. So if we consider that, then we can say 4. So 2 and 4 both were the correct options, correct answers for this question. Okay. So, for this question, that is the number of possible optically active isomers for the following complex is 2 or 4. Is it clear? Hello?
Yes, ma'am.
So, now moving on to the next question. Question number 44. The question says a complex is composed of one chromium ion, three bromides, and six water molecules. Upon addition of excess AgNO3, 1 gram aqueous solution of the complex gave 0.94 gram of AgBr. The molecular formula of the complex is what? Okay, so what is the molecular formula of the complex? The complex is composed of 1 chromium, 3 bromides, and 6 water molecules. And when they are adding silver nitrate with this complex, they are getting 0.94 gram of silver bromide. So what is the molecular formula of the complex that we have to write? So the empirical formula for this complex is there is one chromium, there are three bromides and six water. So chromium, Br3 and six water. So first we will calculate the molar mass of this complex. So here you can see that they have given the atomic weight for all the elements. So for chromium it is 52, 52
And
plus
6 water, ma'am.
I wrote 1. Okay. Yeah, there is 6. There are 6 water. Sorry. So 52 for this. Then bromine. There are 3 bromine. So 3 into 80 and 6 water. So for O it's 16 and H1. So 18 for 1 water molecule. For 3 water molecule it is 3 into 18. Okay. So if we calculate this, this will be 50.
400.
Okay. How much?
400 grams.
Okay. So is it 400 or 346? Okay. Am I doing something wrong? Wait. 3 into 80 plus 10, 3 plus 52. It's 346, right? Please correct me if I am wrong.
346.
Uh,
346.
Okay, so the molar mass for this complex is 346. Now, uh, we will also calculate what is the molar mass of AgBr. Okay, so molar mass of silver bromide. So for Ag, the atomic weight is 108 and for Br it is 80. So it is 188. Okay, this is 188 gram per mole and this is 346 grams per mole. Now, if we find, like here
Ma'am,
they are saying, yeah,
in while calculating the molecular weight, in
sorry, it is 6.
yes, ma'am, then we will get
Oh,
400.
yeah, then it is 400. Thank you. Okay, so in this question, what they are saying is 1 gram aqueous solution of the complex gave 0.94 gram of AgBr. So 1 gram complex gave 0.94 gram of AgBr. So now we will find out that in 1 gram complex there are how many moles of this complex. Okay. So for that the formula is number of moles, we all are familiar with this, is equal to the mass, that is 1 gram, divided by the molar mass, that is 400 gram per mole. Right. So 1 by 400 is 0.0025. Okay. And here also they have given that 0.94 gram of AgBr we are getting. So number of moles in 0.94 gram of AgBr is 0.94 divided by 188 gram per mole. That is equal to 0.94 divided by 188. So this is equal to 0.005. So here we can compare that 0.0025 millimoles, it is giving 0.05 moles of AgBr, which is double of this, right? Now here in this complex, we can see that 3 bromines are present. And we know that if bromine is present outside the coordination pair, then only it can react with AgNO3 and give AgBr. Whatever is, if the bromine is present inside the coordination pair, that is, this is the coordination pair, right? If it is present inside, then it can't react with AgNO3 and AgBr will not be precipitated out. So from this, we can understand that since by using 0.0025 mole of the complex, we are getting 0.005 mole of AgBr. That means for each 1 mole, we are getting 2 moles of the AgBr complex, right? So that means 2 bromines are outside the coordination pair. That is, chromium is there, 6 water molecules are there inside, and 1 bromine molecule is there inside, whereas the other 2 bromines are outside the coordination pair, which are reacting with AgNO3 and precipitating out 2 molecules of AgBr. Okay. So among the given options, that is CrH2O whole 6 Br3, here all the bromines are outside. So if this would have been the molecular formula of the complex, then for 1 mole we should have got 3 moles of AgBr. That is, this value should have been triple. Okay, but that is not the case. So option number A is not correct. In option number B, we can see that 1 Br is inside and 2 is outside. Okay. Okay, here what I wrote is H2O. Yeah. So it will be six coordinated. So five is there and one H2O will be present outside, right? Because we started with six water molecules. So this can be our answer. Like this is our answer actually. And here in this option, they have given one bromine molecule outside. If this was the case, then from 0.0025, we should get 0.0025 of AgBr only, which is not the case. So this is incorrect. And option number D, that is all the bromine is inside, then we would not have obtained any AgBr after this reaction with silver nitrate. So this is also not the option, not the answer. So for question number 44, the correct answer is option number B, that is chromium, five water molecules coordinated and one Br, and the other two bromine and one water is present outside the coordination sphere. So this is the correct molecular formula for this complex. Is it clear?
Yes, ma'am.
Yes.
Okay, so we will move on to the next question. That is question number 31. So question number 31, they are asking that the correct molecular representation of WCP5, CP2 CO2 is where CP is cyclopentadienyl ligand. So this is a very easy question. So here, this is the complex. Okay, tungsten, two cyclopentadienyl ligands, and two carbonyl ligands. Now, what is the electronic configuration for tungsten? Anyone?
6 electron in outermost.
Okay, so it is a D6 system, and cyclopentadienyl, the this is the ligand, cyclopentadienyl ligand. So this ligand can actually have different haplicities. Haplicity means it can like if one metal complex is coordinated like this, then the haplicity will be 4 because it is attached to all the 5 carbon ligands in this case. Also, this can this ligand can bind in this way as well, where this metal center is coordinated to only 3 carbon ligands among the 5 carbon ligands. So in this case, the haplicity is 3. So if it is coordinating in an eta 5 fashion, then it is a 5 electron donor. Whereas if it coordinates in eta 3 fashion, then it is a 3 electron donor. Okay. And carbonyl is a neutral 2 electron donor ligand. Okay. So in this question, they're asking the correct molecular representation of this will be what? So here also, as I always say, if we are given any organometallic question, so we should always first think about that question we will start from 18 electron rule. Okay. So here among the given options, now we will see that which among them satisfies 18 electron rule. As we know that if there are 18 valence electrons, then the complex is the most stable one. So let's start with option number A. Here tungsten is there, so tungsten eta 1 Cp. Okay, here this can also coordinate in eta 1 fashion. As I did not say, that is It is coordinating just with one of the carbon ligands. Okay. Metal can also bind in this fashion. If it is a eta 1, it is binding in eta 1 fashion, then it is a 1 electron donor. Okay. So here they have given this complex eta 1, then eta 3 CpCO2. So this is the first complex given. We will calculate the valence electrons. So for tungsten, it is a D6 system. We are counting it in neutral method. So we won't worry about what is the oxidation state and all of metal. Okay. So tungsten is giving 6 electrons. Since Cp here is binding in eta 1 fashion, so it will give 1 electron, and eta 3 Cp, that means 3 electron will come from this ligand, and carbonyl, we know it's a 2 electron donor. There are 2 carbonyl ligands present. So it will be 6 plus 1 plus 3 plus 4, that is 14 electron system, right? So option number A is a 14 electron system. Now let's come to option number B, which is eta tungsten, eta 1 Cp, eta 5 Cp, and 2 CO2. Okay. So for tungsten, it will be 6 electron. Eta 1 means 1 electron. Eta 5 means 5 electron. And CO2 means 2 into 2, that is 4 electrons from these two carbonyl ligands. So this is 6 plus 1 plus 5 plus 4, that is 16 electron system. So option number B is a 16 electron system. Now coming to option number C, that is tungsten coordinated with eta 3 cyclopentadienyl, eta 5 cyclopentadienyl, and 2 carbonyl. So here it will be 6 from tungsten, 3 from this cyclopentadienyl, 5 from this cyclopentadienyl ligand, and 2 into 2, 4 from this carbonyl. Okay, so this is again 6 plus 4 plus 3 plus 3, that is 16 electron system. 6 plus, sorry, it is 5. This is an 18 electron system. Okay, and then option number D, that is tungsten eta 5 Cp 2 CO2. So here 6 electrons from tungsten, 5 from Cp. There are 2 eta 5 cyclopentadienyl ligands, right? So 5 into 2 plus 2 into 2. So 6 plus 10 plus 4. So here it is a 20 electron system. So this is 18 and this is 20. So it is very easy to now say that which one will be the correct molecular representation. So which one is the correct one?
C.
Yeah. So this was one among the most easy question which came in GATE 2019 paper. Okay. Okay, so we will move on to the next question. So question number 27. The question is, among the following compounds, a normal spinel is option number A, MgFe2O4, option number B, ZnFe2O4, option number C, cobalt Fe2O4, and option number D, copper Fe2O4. So this is a question from coordination chemistry again. And in this question, they have asked that which among the following shows a normal spinel structure. Okay. So for this, first we will discuss about these compounds. So if we are having A, B2, X4. For A, B2, X4 type of complexes where A is one metal, B is B can be the same metal or different metal, metal number two, and X can be oxide, sulfide. Okay. So for these kind of molecules, we can have normal spinel structure, inverse spinel structure, or mixed spinel structures. Okay. So what is the criteria? How we can find out that which which molecule will have normal spinel structure and which one will have inverse spinel? So the way is that, okay. So from where it is coming is that there are two molecules, and in this complex there are tetrahedral and octahedral voids. Okay. So if and here A is present in +2 oxidation state and B is present in +3 oxidation state. So if A2 plus is going in tetrahedral void and B3 plus is going in octahedral void, then the structure which we will get from this will be normal spinel, normal spinel structure. Whereas if we have B3 plus in the tetrahedral void and the octahedral void consists of both A2 plus and half of B3 plus, like half B3 plus will be present in the tetrahedral void and half B3 plus will be in the octahedral void and it along with A2 plus. If the structure is like this, then we call it inverse spinel structure. And if we have mixed spinel that have, like in this molecule, it is mixed of both normal and inverse spinel, then we call it a mixed spinel structure. Now if we look uh, like how we will know that this A2 plus is going in tetrahedral or B3 plus is going in tetrahedral. This we can find out by comparing their CFSE. So what is CFSE? CFSE is crystal field stabilization energy. Okay. So in an octahedral molecule, as we know that these d orbitals are split into two energy cells, that is T2G and EG. Okay. So if I will draw this. Okay. Let's say we were having this 5 degenerate d orbitals and then it's split into this EG and 3 T2G. Okay. So from we know that this difference between the T2G and EG is the del O value, that is crystal field splitting, and in downside, that is in T2G, like this difference is of zero point 0.4 del O, whereas this difference is of 0.6 del O. Okay, so this way we calculate the crystal field stabilization energy. Like if an electron is present in T2G, we will consider zero point 0.4 for that for each electron, and for each electron present in EG, we calculate zero point 0.6 del O for that. So if CFSE value for B3 plus octahedral is more than CFSE value for A2 plus octahedral, then we will get normal spinel structure. Okay, there is some lag between the screen. Okay. If this is the case, then we will get normal spinel structure. Whereas if it is reverse, if the case is reverse, that is if CFSE of A2 plus or octahedral complex is higher than CFSE of B3 plus octahedral, then we will get an inverse spinel structure. And mixed spinel structures we get when we have like both for both the cases for both the metal complexes, the CFSE is same, as well as they have both A2 plus like this A and B will is having a comparable size, and the CFSE value is coming out to be the same. In that case, we get mixed spinel structure. Okay. So here now we will start from complex A. Okay, which is magnesium Fe2O4. So here the two complexes, one more thing which I should say, for main group elements, that is for non-transition elements, the crystal field stabilization energy is 0. So in this case, we have one metal as magnesium and the other metal as iron. So magnesium is a non-transition element. So for magnesium 2 plus, we are having a CFSE value of 0. And for iron 2 plus, not iron 2 plus, it will be iron 3 plus, right? So this is Mg2 plus Fe3 plus. So for iron 3 plus octahedral complex, what will be the CFSE value? The electronic configuration for iron is D6H2, right? So for Fe3 plus, it will be D5 system. So 1, 2, 3. Oxygen is high spin, weak field ligand, so it will give high spin complex, and therefore D5 means 3 into zero point 0.4 plus 2 into 0.6, that is equal to, like, this is minus 3 into minus zero point 0.4, and here why minus, because this is going down, okay, and down in energy. So for this one it's minus. Sorry. So here what is the CFSE value which we are getting for D5? It is 0, right? So for this case it will be 0. So here we can see that both for Mg2 plus, that is A2 plus and B3 plus metal, for both of them the CFSE value is same, which is 0. And also magnesium and iron are having a comparable size. So therefore in this case the structure which we will get is mixed spinel. Okay. Now coming on to option number B, which is ZnFe2O4. Now for this case again zinc 2 plus. So zinc 2 plus is a D10 system, right? And D10 system means all the electrons of T2G and EG are filled. So here also the crystal field stabilization will be how much? Crystal field stabilization energy will be, anyone?
0.
Yeah. And for iron, again here iron is in plus 3 oxidation state. We already found out that for iron in plus 3 oxidation of state, it octahedral complex, it will be 0, right? So in this case also we can see that both A2 plus and B3 plus are having 0 as their crystal field stabilization energy. But here, if we see the periodic table, after iron, cobalt comes, then nickel comes, then copper, and then zinc. Now we all know that if we go across the period, left to right across the period, the size decreases, right? So Zn is smaller than Fe2 plus. Now we were talking about tetrahedral and octahedral voids, right? Now since Zn is smaller and tetrahedral voids are smaller than octahedral voids, now if Zn is going in Zn2 plus is going in tetrahedral void and Fe3 plus is going in octahedral void, then this will be a normal spinel structure. Okay. If these two were having comparable size, then it would also have been mixed spinel. But since in this case there is size difference, the smaller uh, ion is going to the tetrahedral void, and the uh, larger ion, the bigger one, is going to octahedral void. Therefore, it will give a normal spinel structure. So for option number B, it is normal spinel. Now we will C for option number C, that is COFe2O4. Okay, for COFe2O4, cobalt in plus 2 oxidation state, that is, it will be a D7 system, right? Cobalt 2 plus means it is D7 system. Now we will calculate the crystal phase stabilization energy for this, which is 1, 2, 3, 4, 5, 6, and 7. And for iron 3 plus, we know that it is 0. So definitely this CO2 plus will have a higher CFSE than this, because there is 2, like this 5 will cancel out, but then there is minus zero point 0.8 del O. Okay. So therefore, CO2 plus octahedral is having greater CFSE. Like if we are calculating CFSE, the final result, we will take mod of this. So here the crystal field stabilization energy completely is coming out to be zero point 0.8 del O, which is greater than Fe3 plus octahedral. Okay. So then it is following this condition where A2 plus is having, like the reverse of this, A2 plus octahedral is having a higher crystal field stabilization energy than B3 plus octahedral. So in this case, the complex will be will have inverse spinel structure, right? So in this case, it is giving an inverse spinel structure. And now the last option, that is option number D, it is CuFe2O4. Now copper in plus 2 oxidation state and Fe in plus 3 oxidation state. So copper in plus 2 oxidation state is the how many d electron system?
D10,
So no, it is in plus 2 oxidation state, na. That means it is a D9
D9,
system.
D9.
Yeah. Okay. It is a D9 system, and Fe3 is 3 plus is having CFSE value of 0. So here also A2 plus octahedral is having higher CFSE value than B3 plus octahedral. That means it will also give inverse spinel structure. So this is also inverse. So among the given options, we can see that only in option number B, that is Zn Fe2O4, we are getting a normal spinel structure. So therefore, the answer to this question, that among the following compounds, which one will have a normal spinel structure, will be option number B, that is Zn Fe2O4. So option number B is the correct option. Any doubts?
Ma'am, how you compare the size of Mg and Fe in the option one? Uh, so you say it is a comparable size, but
Huh.
how you compare?
So in the periodic table, if we see, wait, Mg and so actually see, magnesium is in group 3 and sorry, not group 3. Magnesium is in third period, whereas this iron is in fourth period. And if we see that magnesium here, it is in group 2, whereas that iron, it is in group 8. So it is difficult to compare their size. So how I got it, you can search their sizes. Okay, so they are almost having a comparable size. So this
Ma'am,
is
one
one.
is Mg is 173 picometers and Fe is 38 picometer.
Is it okay?
It's okay, ma'am. It's okay, ma'am. I think there is a little bit
So when I
size
read
difference.
this also, there was like in mixed spinners actually there are very few examples only. So this was
Ma'am,
also
this type of
given
question,
among.
actually why I'm asking you because this type of question is very confusing. Uh, uh, because in which case we have comparable size, in which case it is not comparable size. It is not easy to determine actually in the examinations hall.
Yeah, so
Just like
what I feel that if you are having something in the same period like this, in this case, it was very easy to compare, right? As per our
yes,
knowledge,
ma'am.
which we know
Yes, ma'am. Yes,
from.
ma'am. That is.
So that is one
But
thing. Also, like you can always go from backwards, right? If you are seeing that this is inverse, and this also you are sure that this is normal, that is another way. But yeah, comparing the size, and we also don't remember the sizes. Okay, that is like
actually,
we
that is my
can't.
point now. Yes,
Yeah,
ma'am.
we
That is
can't.
my point.
So for these questions, I feel there will be always the other options which you will understand that what is that. See, finding inverse and normal spinel by CFSE values, that is very simple. For normal, this one is zinc Fe2O4. This is all. This is a very common example. This I have seen in many question papers, and this is having normal spinel. And one more in these among these is M, like MnFe2O4. Okay, so since you asked, this is also an example of mixed spinel. Okay, so these two complexes, most of the places I have seen that these two are given in the options, and these are mixed spinel. Okay, so I actually don't know how to like exactly compare these two. So I, if I come up with something, I will let you know in the next class.
Thank you, ma'am.
Yeah. Any more doubts? So, in the last class, I discussed about this compound, which is cobalamin. So, there I told that it is a heme protein, but it is not a heme protein. It is having a corin ring and a cobalt center in it. So, it is not a heme protein. I told that it is a heme protein, but it's not. Whoever were there in the last class, sorry for that confusion, but it's not a heme protein. Okay.
I mean, the last class there is a confusion between that there is a orbital contributions and spin
Yeah, that was
contribution.
also there. So for that, it is that if we are having any unsymmetrically filled orbitals, like then only we are getting. Okay, so I will open that. Then we are getting that orbital contribution. Ninth class. This was the question. Right. So we were confused because of this chromium 3, right? So chromium 3 means chromium is a D5S1 system. So chromium in 3 plus oxidation state means D3 system. That is 1, 2, 3. So here we can see that all the electrons are symmetrically filled. Therefore, there will be no orbital contribution. So I think you or someone else pointed out this only, that if the electrons are filled unsymmetrically, if there is anything like that, then only we are getting orbital contribution. So that is correct. So since it is filled symmetrically, there is no orbital contribution, and it is for this one we are getting the spin only value as the magnetic moment, whereas for cobalt it is a D7S2. So cobalt 2 plus is a D7 system. So 1, 2, 3, 4, 5, 6, 7. So here we can see like no, unsymmetry. Like it is not symmetric in the T2G uh, T2G level, right? Two of them are having two electrons, whereas this is having one. So because of this, it will have orbital contribution.
Ma'am,
Okay.
there is another confusion in D7 is there any not mentioned is the high spin or low spins?
Even if it is high spin or low spin, it will be the same only. In that case, then you will have uh, like that
In the high
symmetry
spin
problem in the EG cell. Okay.
in
One,
the high
two,
spin
three,
in T2G is symmetrical.
three. But EG will not be symmetric, right?
Mm, yes, ma'am.
Then that is rising from the EG orbital. So in that case also, whether it is high spin or low spin, for both the cases, we will get this orbital contribution. Okay.
Thank you, ma'am.
Yeah. Anything else? Okay, then that's all for today's class. If you have any queries, you can mail me. So I have already shared that with you. Okay. And now there is one YouTube channel also. The recording links are there, so you can see the live session recordings there. Okay, thank you.